I have tried and failed to shoot this video 4 times. And the main reasons for that is because every time I try to shoot it and I play it back and I edit it and I look at it, I think that it's absolute bullshit. I don't have a very good relationship with math. And this scarred relationship started all the way back in first year when my teacher, Miss Lacroix, introduced the concept of counters to us. Now at 5 years old, I thought that counters were these things. And it was only when I was about 16 and I had a moment and I was like, But by that time, my relationship with math had already been, broken beyond repair, and any hope that my parents may have had for me pursuing a career in math was surely over. And so then I turned to photography and graphic design, and here we are. So the thing with me and math is that I needed to be very, very, how to put it, tangible. Okay, so basically the idea of this golden ratio, the first part of it has to do a lot with psychology, and the second part of it has to do with math that tries to interpret that psychology. And what I mean by that is the golden ratio happens in nature anyway. It happens in plants, in trees, in volcanoes, whatever it is. And mathematicians have tried to look at that and try to understand it. So the first time that the term golden ratio was used was actually in 1815 by a German mathematician named Martin Ohm. And let's take a bit of a turn here, right? So aesthetics is basically the understanding of what makes something look beautiful. And beauty, as defined by modern standards, is symmetrical. Like, we define a good-looking face as a symmetrical face. If the left side and the right side of the face are equal, that speaks to us and says that that person then is good looking. If it is that you have one eye bigger than the other, one eye smaller than the other, then it becomes this idea that that person is now unbalanced, so they don't look as good. Well, that's what kind of gives us this idea of two sides, and a ratio is a comparison of two things. Now, what happens if one side is not the same size or does not have the same equal properties as the other side, but it still looks good? Well, that basically is the idea of the golden ratio. It's the idea that we can observe the relationship between two things that are not equal yet still look good. So why is that? And the fact that this happens in nature kind of erases this whole stupid idea that good looking is only good looking if it's balanced. So in order to come up with the psychology that kind of governs this, there's something called the Gestalt principles. And online, there are a bunch of different places and different sources that have different amounts of Gestalt principles. Now, we don't need to go through each one of them and what exactly all of them do, but the idea basically is that there are different ways of observing things. There are different ways that the brain works when you observe different things. So if it is you see something that is not complete, we can fill it in. If we see something that looks kind of like a face, why is that? If we see something that is continuous, then we can associate it with something else. Like, let's say you had doorknobs in a house, for example, and you knocked out and woke up in that house like 5 days later in a room that you never saw before. If the doorknob was the same as the doorknob that you saw 5 days prior in the same house, then it immediately tells you that maybe I'm in the same house. Basically, all of these principles go back to the idea of survival and giving us a sense of position in the world. Moving on from that now, again, you get the idea of it being an observation, right? So if the Gestalt principles are an observation of how we survive and an observation of nature, then there must be a way to take it a step further. And this is where the math of the golden ratio comes in. The first part of the math of it is something called the Fibonacci sequence. And the Fibonacci sequence says that if we look at 3 numbers, then the third number is the sum of the preceding 2 numbers. And there's a sequence for that. Hold on. So let's start with 1. Let's go to 2. 1 plus 2 is equal to 3. If we look at these two, then 3 plus 2 is equal to 5. If we go again and we look at these two, 5 plus 3 is equal to 8. We go one more, 8 plus 5 is equal to 13. And since this continues for infinity, it gives us the ability to observe that something is happening here. There's a pattern that's happening between these numbers. And as these numbers go up and they continue to, however big you want to make it, the mathematicians have observed that there's a relationship that's happening every time you add up the last two numbers and come up with the next one. And that relationship stays consistent throughout this entire sequence. And they've boiled that down to a number. And that number is 1.618. What does that mean for art? What this thing is saying is that if we take this 11 and then we divide it by 1.618, then we get 6.798, which rounded off should be 6.8. So if you think about how the math works, right? This is object number 1. This is object number 2. If I put these two objects side by side, there is now a relationship between object number 1 and object number 2. Obviously, these two are asymmetrical, they're unbalanced. It means that one is bigger than the other, but according to this math, if I put them together like this, that they still look good together for a reason, and that reason is the math of the Cooldown ratio. Now, let's go back to teachers, let's go back to math, right? Why on earth would I ever need to know? So there are in fact real life applications to this thing, right? As much as I thought it was absolute nonsense. So let me show you. Keep this in mind, right? Keep this shape in mind. Let's go see something. This is a chair. Now, according to this piece of math, there's supposed to be a relationship between the black part, which is actually 14 inches high and 24 inches wide, and the wood part, which is 17 inches high. So 17 inches high divided by 1.618 is equal to 10.5 inches. Just for the black part, 24 inches divided by 1.618 is equal to 14.8 inches. While it didn't apply necessarily to this part, to this part, it did apply to the relationship between the width of the chair and the height of the chair. All right. So in order to relay my findings, I have created this very comprehensive diagram. The very comprehensive diagram. This was a fig leaf, and this was 47 inches high. This was the Hana fig, and this was 24 inches high. This is a fig, and it was 6 inches long. So now we're going to work out what is the relationship between the height of the fig leaf and the height of a Hana fig. So if we go 47 inches divided by 1.618, ooh, so I mean 29 inches, I mean, is nature, it's not going to be exact, right? So that ain't too far off from 24 inches. So we see there is a golden ratio relationship between the size of the fig leaf and the size of the Hana fig. Now the second relationship we want to look at is the width of the Hana fig, which is 13 inches roughly, and the height of the Hana fig, which is 24 inches roughly. So we're going to go 24 divided by 1.618. Ooh. So if this is 14.8 inches and the width of the Hana fig was 13 inches, then I mean we could, give or take a couple inches. So we see again the golden ratio working for the width and the height of the fig. Okay. So we have tested this with this chair and we've tested it with the green fig outside. One is man-made and one is natural. And in both cases, we've seen that the golden ratio exists. We only had to observe in order to find it. And I think with the chair, that the height of chair actually is not a very good indication of it, because heights of chairs is like a standard thing. So they can't really interfere with that too much. Otherwise, like if you try to sit on a chair, you would like drop and get injured or whatever. So chairs still follow a more standard sizing. However, with the width and the height of the black part of the chair following the golden ratio, and the fact that the design of the chair consists mostly with the black part of the chair, then it makes sense. Even though Miss Lacour kind of set me off kind of bad in first year, no, it's pretty cool. It's interesting. Like seeing this happen like in real time was really interesting for me. So in conclusion, the golden ratio, if we had to apply this to design, if we had to apply it to photography, if we had to apply it to anything that we are artistically exploring, we could see that based on our experiment and based on our observation, that the golden ratio is merely an attempt to recreate the natural, beautiful aesthetic of nature. Like if we can make things that look natural, then they present themselves as aesthetically pleasing because they fall into the natural scheme of things that we see outside. If we apply this to buildings, if we apply this to furniture, if we apply this to car designs, then it makes the design feel more connected. It's supposed to make us feel like it's not like a sore thumb sticking out, like it's something that we can actually use and interact with in a natural way. And translated into how humans naturally use objects, that's the study of ergonomics. But now we know.